Welcome to The Explainer. Today, we're going to pull back the curtain on the magic behind all those incredible AI-generated images, videos, and sounds you see everywhere. We're going to break down how a computer can start with pure, random static and somehow turn it into a masterpiece. Okay, so let's kick things off with something you've probably seen a million times by now. A simple text prompt that creates something absolutely amazing. You start with this simple, almost kind of crazy idea, an astronaut riding a horse. You just type it in, and in a few moments, the AI takes that text and transforms it into this stunningly detailed image that looks like it was pulled right out of a dream. So that's the big question, right? How in the world does this even work? Well, the answer is this really powerful idea called a diffusion model. And this isn't some far-off sci-fi stuff. This is the tech that's already powering all the tools you've heard of. From images to video and even to sound, they all, believe it or not, boil down to a surprisingly simple concept: reversing chaos. So how does a machine actually learn to create something from nothing? The intuition behind it is honestly brilliantly simple, and it actually comes from physics. This is it. This is the core concept right here. The AI basically watches how something structured, like a picture, can dissolve into total randomness, step by step. Then it just learns how to run that process backwards. It's like magically unmixing the ink from the water, which is just mind-blowing. So in more technical terms, what we're talking about is a type of generative AI called a diffusion model. You can think of it like a two-step dance between order and chaos, and really, getting this forward and reverse process is the key to understanding the whole thing. Okay, so here's how it works, broken down. It's a two-phase process. First up, you have the forward process. This is the learning part. The AI takes a real, clean image and just slowly, step by step, adds noise to it until it's nothing but static. Then comes the reverse process. Now here is the really clever part. The AI isn't trying to predict the original clean image. No, it's trained to predict only the noise that was added at each step. So by getting incredibly good at seeing and removing chaos, it learns how to build order.
All right, so what kind of digital brain is actually doing all this heavy lifting, this complex denoising work? Let's pop the hood and look inside the engine.
For a long time, the star player here has been a neural network architecture called the U-Net. And what's really fascinating is that it wasn't even designed for creating art. Its original job was way different. It was built to identify individual cells in medical scans.
And it turns out the U-Net's design is just perfect for this task. You see that U shape? One side, the encoder, shrinks the image down to understand the big picture. The what. Is it a face, a car? Then the other side, the decoder, builds it back up, restoring the where. But the real secret sauce? These skip connections that jump across the U. They pass all those little fine-grained details from the early stages to the later stages, and that's what makes sure the final image is sharp, not just a blurry mess. And finally, time embeddings basically tell the network exactly how much noise to look for and remove at any given step. This whole setup is why it works so well. But as always in AI, the field is moving fast.
Lately, though, we're seeing a big shift. Transformer-based architectures, the same kind of tech that powers things like ChatGPT, are starting to take over. Instead of looking at pixels in a grid, they break an image into a sequence of patches. And their big advantage? They scale incredibly well. That scalability is what's really powering this next generation of models.
Okay, so here's the really cool part. This whole core idea of denoising, it's incredibly flexible. We're not just talking about static images. You can adapt this same idea for all kinds of media. For video, the big challenge is making sure things stay consistent from one frame to the next, right? So the models use these 3D architectures that think in stacks of frames. It's pretty cool. For audio, the process is even more clever. A sound wave gets converted into what's basically a 2D picture of its frequencies. That's called a spectrogram. The AI denoises that picture, and then a separate tool called a vocoder translates that clean picture back into the sound wave you actually hear.
And this adaptability is exactly why diffusion models have become such essential tools for, artists, filmmakers, game designers, pretty much anyone in a creative field. Need a super specific sound effect or a quick visual concept for a storyboard? These models can just whip it up for you. All right, so we get how they work now, but where do diffusion models actually fit in the bigger picture of generative AI? Well, if you compare them to older methods like GANs, you might remember those, they work by having two AIs basically fight each other. Diffusion models just produce way higher quality and more diverse results. Plus, training them is much more stable. But there's always a but, right? There's a big trade-off: speed.
Yeah, creating a single image isn't a one-shot deal. It requires all these iterative denoising steps. We're talking 50, 100, sometimes even more, and that makes the whole process a lot slower than those single-pass models. Researchers are working like crazy to speed this up, but for now, it's a key challenge.
And this brings us to what might be the most important takeaway of all. Models like Sora, you've seen the videos, they can create these stunningly realistic scenes, but, and this is a big but, they don't understand things like physics or cause and effect. They are just incredibly sophisticated mimics. They're masters at recreating patterns they've seen in their massive training data. So they know what shattering glass looks like, but they have no concept of why it shatters.
So that leaves us with a huge question. As these models get faster and smarter, where do we draw the line? What's the difference between a tool that just mimics reality and one that actually starts to understand it? That distinction between mimicry and genuine understanding, that's probably the most fascinating question we're facing as this technology just keeps evolving at a wild pace.